All right, it's 1 o'clock, so let's go ahead and get started today. Afternoon, everybody. How's everybody doing today?
Pretty good.
Good, good. Yeah, good. It's week 9, so the semester's really getting away from us now, so it's good. Okay, so on last Thursday, I think the last thing we did was talk about the project. So hopefully everyone got to see the project spec. So I think I finished those Thursday night, and I saw a little bit of activity on the Discord channel of people getting groups together. But now that everyone's kind of hopefully had a chance to look at it, are there any questions about the project? Okay, so I plan to have the sign-up sheet probably up near the end of this week. So hopefully, if you have your group together, that's great. You can start reading through the different case studies that I have on the specs already. Or if you want to do something else, definitely, try to run that by me, before the end of the week. I think that would be probably the best thing. So once the sign-up sheet goes live, it's unfortunate. I think the way I'm going to have to do it is it's going to be first come, first serve. So I'll basically let everybody know when the sign-up sheet is going to go live, and I'll send everyone the link. And then basically you'll basically, I think the best thing to do is have, one person designated from your group sign in onto Google, and then log into the Google sheet, and then input the, and then just sign up for the case that you want. But remember, because it's first come, first serve, try to have like maybe 2 or 3 backups just in case you don't get the one that you want, okay? So it'll be just like, buying tickets for a concert or buying tickets for Comic-Con. So, hopefully it'll be a little bit less frustrating than that, but it's, I think that's the system that I did last year, and I think, should work okay this year. I don't think there were too many cases of, a group didn't get a case that they want. I think there was only one group that told me that they didn't get that. So, and I added a few more cases this time too. So hopefully, everyone gets to do something that they at least are interested in. Okay. So besides that, are there any questions of what we covered last week? So today the plan is we're going to cover a new set of lecture notes on replacement analysis. So are there any questions on, I think what we finished last week with taxes? Anything questions on that, or questions on the homework? Okay, so let's go ahead and get started today. Okay, so we're starting a new set of notes today. So we're nearing the end of our time with economics, and so this is I think the second to last topic. And the idea with this set of lecture notes is called replacement analysis. And so replacement analysis, the name is fairly self-explanatory. And so the idea is that, we're going to use basically our economic techniques that we've learned so far to determine, when is the best time to buy a replacement machine. Okay. And so for a lot of the problems that we've been dealing with so far, we've bought machines, and there's always been a caveat with them that said, this machine is only going to last maybe 5 years or 6 years or something like that. Okay? And so the time frames that I've given you for all these problems is that's called the useful life. Okay? And so the useful life, if we can give it kind of a more concrete definition this time, the useful life is defined as the amount of time that you can use an asset. Okay? Okay. And so the kind of the assumption that we've been working under, for all this time, is that when we say that a certain machine has a certain useful life, we're kind of assuming that the asset is equally productive at the beginning of its life as it is at the end. Okay? But I think, everyone, at this point kind of knows that that's not necessarily true for, for devices or machines that you keep for many, many years, right? So you think of your car, you think of your computer, you think of your phones, eventually, all these things get replaced, and so basically, just because you can use an object for a really long time doesn't mean that you really should, right? So anyone who has a car that's, over 11, 12 years kind of knows this, but you could still use it, but it just doesn't mean that it should. Okay. So what does this mean concretely for for engineering machines? And so for engineering machines, as machines get older and older, first of all, they could become less productive. So they might produce less revenue. Okay. Okay. Another factor to consider is that, the older a machine gets, or the older an asset gets, it's going to take more money each year to maintain. Okay. And so both of those factors kind of make it, less desirable to hang on to something for a long time. Okay? Another factor to consider is that, if you keep, a car, say for, a long period of time, a newer car will come out each year, and each new car will have an increased, capability. So it's the same thing for engineering machinery too. And so the longer you keep, a certain computer in your computer lab, you're kind of also paying, you're not only paying to maintain that computer itself, but you're also paying an opportunity cost by not upgrading to, higher capabilities. Okay. And so what we're going to do this week is we're going to basically apply all of our economic knowledge to basically take all these factors into account and to determine, when is the best time to replace a machine. Okay. And so we're going to be doing this within the context of, engineering projects. So this is an engineering economics class, but I think this is something that's, really relevant to your personal lives too. So you can use this to determine, when's the best time to buy a new laptop, or when's the best time to buy a new car, or buy a new iPad or something like that. Okay. So, I want you to kind of keep that in mind as we go throughout this week, that it's, even though we're doing this with numbers and with examples that are, relevant for that, but, it's also relevant for your personal life. And also, a lot of other industries, work with this kind of knowledge as well. So I think at the end of the week, I think we're going to do an example for a bakery too. And so, determining when they should buy a new oven for the bakery. Okay, are there any questions on this? Okay. Okay. And so that's the useful life. So we're going to contrast this with the kind of a new, I think, a new mindset for how to think about how long to keep an asset, and that's the economic life. Okay. So whereas the useful life, that's how long you can keep an object that's, it will theoretically still be able to work. And then the economic life is the amount of time that an asset should be kept that minimizes the cost of ownership. Okay. And so the last part of this definition is key. And so basically the idea with determining replacements is that you want to keep your asset for just long enough that the amount of money that you're paying per year to maintain it or to own it is minimized. Okay? And so in economic life, there's kind of two competing factors in play. Okay? And so both of these kind of pull the economic life. One pulls it, you want to stretch it out more, and the other one, kind of encourages to stay small. Okay? And so the first one that we'll talk about is, the initial cost. Right? And so in particular, we're talking about spreading out.
Oh, you're muted.
Yeah, he's muted now.
Hey, sorry everybody, my internet crapped out for a second. It's been happening a lot lately for some reason, but everyone can hear me again, right?
Yes,
Yeah.
sir.
Okay, great. Yeah, sorry about that. I think my internet's been having a lot of issues, but we're back. Okay. And so, the first thing that, we're going to, for the first factor that we're going to consider with economic life is the initial cost, right? And so the initial cost, I think, is pretty intuitive to understand. And the idea behind it is that, if you buy, say you buy a certain piece of machine for a lot of money, the longer you keep that machine, the more that cost is kind of worth it. Okay? And so the way I like to think about this is, you take your initial cost and you want to spread that out over as many years as possible. Okay? Okay. And so for this factor, it's obviously it's better to keep your asset for a longer period of time. Okay. Because the longer that you keep your asset, the more that initial cost gets spread out. Okay. And so the other competing factor that you want to consider is the fact that the longer you keep an asset, the maintenance and upkeep costs will increase. Okay. And so, we've seen this in previous examples too with our gradients, right? And so, for a lot of assets, each year that you keep it, your maintenance costs are going to keep going up and up and up. Okay? So for, trying to maintain like your 12-year-old car, in year 12 is going to be really expensive just because, you probably have to fix a ton of stuff on the inside. Okay. And so with this factor, it's actually, in order to minimize the upkeep and maintenance costs, it's better to keep your asset for a short amount of time. Okay. And so the fact that we have these two competing factors like this kind of implies that there's a sweet spot for the amount of time that you should keep your piece of equipment. Okay. And so computing that sweet spot is what we're going to be doing. Okay. And the way that we're going to compute this is or I'll give you kind of a preview of our calculations, is that we're going to be computing basically a metric for if we kept this piece of machine for 1 year, 2 year, 3 year, 4 year, how much is it going to cost us? Okay? And the way that we quantify this is that we usually do it in terms of EUAC. Okay. And so remember, EUAC, that was from our unit on annual cash flow. And so the nice thing about EUAC is that it's kind of indifferent to the amount of time that you're doing it, because this is the cost that happens every year. Okay. And so since we're considering all different time periods for which we're going to keep our asset, EUAC is kind of a very natural and very convenient way to do this. Okay. So another way to kind of express this EUAC is the annual cost of ownership. Okay. And so what we want to do is we want to find the amount of time that minimizes our EUAC. And so with that amount of time, that's the least amount that we would pay per year in order to have this asset. All right, any questions on that before we jump into an example? Okay. Okay, so let's do an example. Okay, so for this example, let's say that we purchased a machine and it has an initial cost of $7,500. Maintenance costs are going to be $1,200 per year. Okay. Plus, it's going to increase by $900 starting in the second year. So there's going to be a $900 gradient. Okay. And so if we assume that our interest rate is 8%, okay, and then we assume a useful life of 10 years, so this machine will last at most 10 years. So given that information, we want to determine the economic life for this machine. Okay. The economic life, and we want to determine the minimum EUAC. Okay. Okay. And so the best way to do these problems is to do it with a table. So a lot of the things in the second half of the economics class we're going to do in tables. But before we do that, let's come up with the formula to compute our EUAC. Okay. So remember, with EUAC, we're basically going to take all of our cash flows and then convert it into a uniform series. Okay. So let's go ahead and do that. So everything here is a cost. So we're all going to keep things the same value. So we're not considering revenue in this case. And so the first thing we have is our initial cost. So our initial cost is $7,500. Okay. Right, so to convert this to a uniform series, we need to do not P over A, we need A over P. Okay. Our interest rate is 8%. Okay. And then we don't know the N yet, because the N, that's what we're going to determine. Okay. And so we're going to evaluate this at N is equal to 1 all the way through 10. All right, to this, we're going to add our gradient. So our gradient is 900. Okay, so in order to convert this to an A, we have to multiply by an A over G factor, 8%, and N. Okay. And then to that, we're going to add our maintenance cost, which is just $1,200. Okay. And so that's our formula for EUAC for this problem. And we're going to evaluate this at each year. Okay. Okay, so let's go ahead and make a table. So I'll probably start it on this table and then, or start on this page and go on to the next one. Okay. So I'm gonna do the first 5 years here. Okay. And I'm gonna split this up into all the different components actually. And so you don't actually have to make this full table every single time, but I'm doing it for this case just to kind of illustrate this. Okay. Okay. And so what I've done for each of the different years, we're going to compute each of our different cash flows expressed as a uniform series. Okay. So first we have our initial cost. Then we have our maintenance, which is our constant one, and so that's our 1200. Okay. Let me throw some color in here. Okay. And so in this first column right here, I'm basically going to compute 7500 times A over P 8% N for various values of N. Okay. And this next column is just going to be 1200. Okay, because that's our constant maintenance costs. And then in the third column, I'm going to compute our 900 A over G 8% N for various values of N. Okay, so let's start with the initial cost. Okay, and so if we evaluate this A over P 8% N at N is equal to 1, then we get 8100. Okay. We evaluate it at N is equal to 2, we get 4206. Okay. We evaluate it at N is equal to 3, we get 2910. Okay. We evaluate it at N is equal to 4, we get 2264. Okay. And then at N is equal to 5, we get 1878. Okay. All right. And so our maintenance cost is going to be constant every year, or at least this part of it. So we're just going to write 1200 in each row.
Professor, you're just applying N to each term, right?
Yes. Yeah. Mm-hmm. Right. And then finally, we have our gradient cost. So this is going to go up each year. Okay. And then so in order to get our total EUAC, we're just going to simply add across the rows. Okay. All right. And so if we keep the machine for 1 year, our cost of ownership is going to be 9,300. Okay. If we keep it for 2 years, our annual cost of ownership is going to be 5,838. Okay. Then 4964, 4728. Okay. And 4739. Okay. Okay. And so you can continue on with this calculation for N is equal to 6, 7, 8, 9, and 10. And normally you would do this for, for the full problem. But I want you to take a look at this entry right here. Okay. So remember, we want to compute the minimum or the amount of time that we're going to keep this piece of equipment that minimizes our EUAC. Okay. And so if we look at the last column here, we need to find the minimum value here. And so our minimum value in this case is 4,728. Okay. And that occurs when we keep the machine for 4 years, right? And so what this analysis tells us is that the economic life for this piece of machinery is 4 years, okay? And then if we keep it for 4 years, then the equivalent, cost each year to own it is going to be $4,728, okay? And if we keep the machine for any other period of time, the annual cost of ownership is going to be, greater than this. And so if we look at kind of the first 3 years here, so if we keep it for the first 3 years, you can see that, the cost is higher because our initial cost hasn't decayed enough yet, right? Or it hasn't been spread out among any other enough years. Okay. But then if we keep for the machine longer than 4 years, so for 5, you can see at this point, the maintenance costs are really starting to catch up a little bit. Okay. And so, if we keep it more and more, then the maintenance costs are just going to get, higher and higher and higher. So it's not really beneficial for us to keep it any more than that. Okay. Okay. Any questions on that?
Will we ever factor in the depreciating salvage value?
Yes. So actually, that's what we're going to do later on today's class. That's a great observation. Yeah. So what that comment was that, that's another factor to keep in mind when you're computing this replacement analysis too. That the longer you keep a machine, it's going to sell for less and less and less. And so that's another factor that that we're going to account for when we're doing our replacement analysis. Yeah. Okay. Okay, so that was a pretty simple example, but it kind of showed you, it kind of illustrated those two competing factors where, when you buy a machine, you want to keep it at least for some amount of time so that, your initial cost is spread out enough among the years, but you don't want to keep it so long that the maintenance costs just kind of get ridiculous. Okay? And so, if you draw out kind of the graph, so by nature, I'm a kind of a graphical math guy, so this kind of helps me a lot. And so if we graph the EUAC versus N, okay, the graph will almost always look like this. So it's going to start high at first, right? And so the fact that it starts high right here has to do with the fact that, we haven't spread out our initial cost enough. Okay, so here for low values of N, initial cost dominates. And then we compare that for higher values of N, like maybe up here, okay? And so for later N's, the maintenance cost dominates. Right? And so what you're looking for in this replacement analysis is something that's kind of right in between them, right? And so you want to look for the point where this EUAC is minimized. And the location where this EUAC is minimized, that's our economic life. Okay. So that's kind of just a graphical way to view this. So it's always going to look like this. I think in the book, what they call it looks like a bathtub graph, where you have a very steep decline near the beginning because the initial cost kind of decays pretty rapidly, but then you have kind of a the graph kind of comes up later on because your maintenance costs are there. Okay, so let's actually talk about salvage values and overhauls actually. So these are kind of two wrinkles that you can throw into these problems as well. Okay. So kind of, like was mentioned, so building off our last unit on depreciation, these assets will generally lose value over time. Okay? And so, another way to express that is the longer you keep an asset, the lower its salvage value is going to be. Okay. And so, you know, we need to account for this too. So we can definitely, you know, account for this into our economic life calculations. But remember, you know, economic life, we compute EUAC. So, you know, each year, the way that we can compute our salvage value is to get the salvage value for that year. You know, we can use some depreciation rule, or you can use some other rule, and then we need to convert it into a uniform series. And this is going to be something that we're going to subtract from our EUAC, right? So our EUAC, member, is a cost. And so any kind of benefit that we get from selling the asset, you know, we're going to subtract that from our costs. Okay. Okay. So that's salvage cost. So you know, salvage is you know, it's a little bit annoying to deal with, but you know, it's relatively, at least intuitively, straightforward. Okay? And so overhauls kind of present a little bit more of an interesting situation, right? So if you remember, overhaul costs are these kind of one-time costs that can happen sometime in the future. Okay. Okay. And so the interesting thing about it is that you might not even see the overhaul cost, right? And so, you know, I think we did an example before where, you know, say that you're purchasing a crane for your engineering company, and there's an expected overhaul cost in year 5, right? So there's like a major maintenance that needs to occur. But if you sell your crane in year 4, you know, before you even get to that overhaul cost, you're not even going to incur it, right? And so the overhaul costs only really occur if you keep it past its date. Okay. And so when we draw our tables for this, it's going to look a little bit strange because, you know, for the overhaul costs, you know, it's going to be 0 for a lot of the time because, you know, if we don't keep the machine long enough to incur that overhaul, then we're not even going to see it. But if we do keep it past the overhaul date, you know, we're going to incur this cost. And then once we incur that cost, we have to spread it out over all the years because remember, we're computing an EUAC. Okay. And so to compute the EUAC associated with an overhaul, often it's going to require, you know, a double conversion because it's an irregular cash flow, kind of like, you know, a lot of what we saw for the first midterm. And so I have a formula for that on the next page. But before I get there, are there any questions on this? Okay. Okay. And so to compute the EUAC of an overhaul, and so we need to do multiple conversions for this, right? And so let me kind of just show you just a brief cash flow diagram just to illustrate this. Okay. And so let's say that we have an overhaul cost that's expected in year 3, right? And so this is what it would look like kind of in a standard cash flow diagram, right? So we would have kind of a future sum that has a value of F. Okay? And so what we want to do is we want to convert this into a uniform series that not only spans up to year 3, but that spans over the entire timeline. Okay? So we want to basically compute something that looks like this. Okay? Okay? So here we have a uniform series up to year 3. So if we just directly converted this F into an A, this is what we would get. But what we want instead is we want to spread this out over the entire, you know, time. Okay? And so in order to do this, you know, we need to do multiple conversions. Okay? And so the formula that we have for this is given by the following. Okay, so we have EUAC is equal to F. And so F right here, that's our overhaul value. Okay. First thing we're going to do, we're actually going to convert it into a present sum. Okay, so we're going to do P over F, I, which are interest rate. Okay. And then the N that we're going to evaluate this is the time at which the overhaul takes place. Okay, so that's what N overhaul is. So in this particular just diagram right here, N overhaul is going to be 3. Okay, and then once we've computed this this factor, then we can spread it out over the entire period of time. Okay, so we're going to take this present worth, and then we're going to convert it to an A. So we're going to do an A over P factor, our interest rate, okay, and then whatever the current time that we're looking at. Okay. 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 And so that's the formula that we're going to use. Okay. But remember, you know, the overhaul only occurs if we've already passed this date. And so we're going to use this formula only if N current is greater than or equal to N overhaul. Okay. And so what that means is that the overhaul is actually going to happen. Okay. But if N current is less than N overhaul, okay, the EUAC associated with the overhaul cost is going to be 0. Okay. Remember, the reason for that is just simply because the overhaul cost just hasn't occurred yet. And so if we sell our machine or we get rid of it or we replace it, you know, before the overhaul takes place, then we don't even have to worry about it. Okay. All right. Any questions on this? Oh yeah. What's up?
Could you write out the greater than one?
Yeah. Yeah. So we're gonna apply this one when only if N current is greater than or equal to N overhaul. And so basically the year that we're considering for the EUAC calculations, that's past the overhaul date. So that's going to be past the time when the overhaul takes place. But otherwise, you know, if it's less than that, then we just simply take the EUAC associated with just the overhaul to be 0. Okay. Any more questions on this before we jump into an example? Okay. Okay. And so again, let's consider a machine. You can see at this point of the semester, I'm getting a lot less creative. Okay. And so this machine has an initial cost of $18,000. And so our maintenance right, so we have two aspects of it. And so we have our constant maintenance cost, so it's going to be $900 per year. Okay. And so in addition to that, we're going to have a $500 gradient. Okay. And so each year after the first year, you know, the maintenance costs are going to increase by $500. Okay. Right. In this case, we're going to consider a salvage value. And so the salvage value for this is going to be $5,000 if sold at year 1. Okay, so we use the machine for 1 year, and then we can only sell it for $5,000. So we're kind of getting ripped off here. So in that 1 year, the machine had already lost $13,000 worth of value. So it's, you know, kind of like a car. Okay, and so, you know, this is going to go down every year, and it's going to go down by 10% each year after that. And so in addition to this, in the 6th year, it's expected there to be an overhaul cost of $3,240. Okay. Okay. And so in this case, we're going to assume an interest rate of 8%. Okay. The useful life is 10 years. Right. And so we want to compute, just like we did last time, the economic life and minimum EUAC. Okay. And so once again, you know, I'm gonna construct a table to for this example. But before that, let's take all of our cash flows in this problem and then convert them into a uniform series. Okay. All right. So let's start with our initial cost. Okay. So our initial cost here is $18,000. And so to convert this to a uniform series, we're going to do A over P, 8%, and then N. Okay. Right. So pretty simple. Next, we have our maintenance. And so our maintenance, we have a constant $900 per year. Okay, so that's already in a uniform series format, so we don't need to convert that. Okay. And then to this, we're going to add 500. And since this is a gradient, we need to convert this. So it's going to be A over G, 8%, and N. Okay. Okay. For a salvage value, we know that we start with a salvage value of 5,000. But remember, this is a salvage value, so it's going to be a negative cost. So we're actually going to put a negative here. Okay. So it's going to be negative 5,000. First thing that we're going to do is we're going to account for its decrease. Okay. And so since we know that the salvage value is going to go down by 10% each year, one way that we can express that is we can multiply this by 0.9, okay, and then raise it to the power of n minus 1. Okay? And so this is kind of an elegant way to do this. So each year our salvage is going to you know, lose 10% of its previous value. Okay? Okay? And since this is a future sum that's going to occur at the end, we only have to apply just one conversion factor. So it's going to be A over F, 8%, and N. Okay. All right. And so in this case, oh, go ahead.
You multiplied that negative 5,000, right, by 0.9?
Yeah, so 0.9 raised to the n minus 1. So, and so what that's basically going to allow us to do is it allows us to compute kind of the lowered salvage value each year. And so if we have n is equal to 1 in this case, you know, we have 0.9 raised to the 0 power, which is just 1, right? So that tells us our salvage value in year 1 is going to be 5,000. But if we have n is equal to 2, then we have 5,000 times 0.9 raised to the first power. And so that's a 10% decrease over the previous year. And then basically this exponent of n minus 1 allows us to kind of quickly compute what the salvage value is for any value of n. Yeah. And so I think, you know, if you want to compare this to our depreciation rules, this is probably closest to the double declining balance, where the salvage value decreases by a set amount each year, by a set rate each year. Yeah. Except that rate in this case is 0.9 and not 2 over n, which is what it was before. Okay. And then finally, we have our overhaul costs. And so we have two different cases here, right? And so our first case is if n is less than 6, okay? Right? And so if n is less than 6, then we haven't incurred our overhaul costs yet. So our overhaul is just going to be 0 in that case, okay? But if n is greater than or equal to 6, then we have to pay our overhaul. You can see here our overhaul cost is 3,240. So we have 3,240, okay? And we're going to apply the formula that we have on the previous page for this. So first thing we're going to do is we're going to convert this to a present sum. Okay? So we have P over F, 8%, and 6. Okay. And so remember, we're using 6 in this expression right here because that's the year that the overhaul takes place. Okay. Okay. And then in order to convert this to a uniform series, we have to take that present sum and spread it out over the n years. We multiply by an A over P, 8%, and n. Okay. And so these are all the costs for each, each of the different parts. And then now we're going to put this in a table so we can compute our minimum EUAC. All right, any questions on this?
Professor?
Sure, what's up?
Then what's the point of having 10 years written?
So 10 years, that's the maximum amount of time that we can keep it. So last time I cut it short because I knew the answer was 4 and that I ran out of space. But in this one, I'll show you basically all 10 years. So we're going to compute the minimum EUAC for 10 years, and then what we'll find is that the economic life should be less than 10 years from that. But the absolute max that we can keep it is 10 years.
Yeah. Oh, okay. Thank you.
Mm-hmm. Okay. So let's go ahead and start drawing the table. Okay. Okay, so we have one column for the year, and so this is going to go 1 to 10. Okay. All right, so we're going to have another column for the initial cost. We're going to have another column for the maintenance. Another column for the salvage. Another column for the overhaul. And then finally, in the last one, we have a column for the EUAC. Okay. Okay, so let's start computing these. So remember, these are all of these things converted to a uniform series. So we're basically going to apply all the formulas we have on this previous page to each of the columns in our table. Okay. All right, so let's start filling it in. So for the initial cost, we're going to start in year 1 at 19,440. Right. Then if we keep it for 2 years, our initial cost is going to be 10,094.4. Okay. That's going to be 6,984. Okay. So I'm going to go ahead and fill in kind of the rest of this. Okay. And this table is in the lecture notes too. So if you want to look at that instead of writing down all these numbers, I think that's probably a good idea too. Okay, so those are all the initial costs for each of the different years. Okay. All right, and so you can see just like from the previous example, the longer we keep our asset, the lower the EUAC is for the initial cost, because we basically spread out that cost over lots and lots of years. Okay? So the initial cost only happens at the beginning, and the longer we keep it, the more that gets spread out. Okay? All right, so now let's do the maintenance. So we're just going to start at 900. then 1,140.5.
Is that 1374 or 1314?
It's 1374. Okay. So there's our maintenance cost. So you can see it had the opposite trend of our initial costs, that these are going up with time. Okay. All right, so now let's do the salvage. Okay. And so we sell at the end of year one, we get $5,000. But then the more time has passed, the less we're going to get for that money. Okay. And so there's two things that are going on with the salvage value. So first of all, the actual sale price is going down. And then, we're also keeping it for a longer period of time. And so since we're converting this to an EUAC, it has the same effect as our initial cost. So that salvage value, the longer we keep it, the more years that gets spread out. One more. Okay, so those are all the salvage values. Okay. And now for the overhaul. So remember, the overhauls are interesting. So if we only keep it for 5 or less years, then we're not going to incur the overhaul. So for years 1 through 5, we're actually going to have 0 here because we haven't paid the overhaul yet. But starting in year 6, once we do pay the overhaul, that's when we actually start to incur these costs. Okay. And so those are all the different costs. Okay. And so just like we did before, we're just going to add across the rows right here in order to get our EUAC. Okay. All right. So let's start from the top. So our EUAC, if we keep for 1 year, is going to be 15340. Okay. And so you can see, our EUAC is rapidly going down from here. Okay. So after all that writing, we finally arrive at the answer. Okay. And so let's look at the last column there and find the minimum value. And so if you look for the minimum value, you should see that it's in year 9. Okay. And so for this problem, the economic life is going to be 9 years. Okay. Okay. And so economically, it makes the most sense, though, to keep this machine for those 9 years, right? And then the minimum EUAC that's associated with this is 5,681. Okay. And so keeping this machine for 9 years basically says that we're going to pay $5,681 per year in order to own this machine, okay? With all the factors kind of taken into account. Okay. All right, any questions on this example here? Okay. Okay, so that's so that example right there, and in the past 2 examples has to do with what's called economic life analysis. Okay? And so that's actually only part 1 of how to do a full replacement analysis. So part of a replacement analysis is to see what's the most what's the optimal amount of time that we can keep this machine. Okay. Okay, so 2 more notes before we actually get into full replacement analysis for 2 other costs that you can to consider. Okay? And so you can all, in addition to basically that last example, you can also specify a cost that that's associated with the chance that something could break down. Right. And so this, I think, is kind of a natural way to kind of think of it, because a lot of times you purchase a machine and you really don't have any idea about how long this is, or when this might actually break down, right? So I know people who get in the car every day and they said there's a 25% chance that my car is just not going to want to start today. And so you can actually quantify this. So there's lots of different ways that you can do this, but one kind of very basic way that you can do this is you can take the percentage chance that something's going to occur. Okay? Okay. And then you can multiply this by the cost that it's going to take to fix it if that something goes wrong. Okay. So just a very quick example. So let's say that you think that each year that you use your car, there's a 5% chance that something really terrible is going to happen. Right. So, and that major something is going to be, in this case, your car getting totaled. So, hopefully, you're safe and everything's okay. But, if your car gets totaled and you're okay, you're probably going to need to buy a new car. And so you can add an additional EUAC that's associated with this by taking 5% and multiplying that by the cost of a new car. So in this case, it's going to be 0.05. And let's say that the cost of a new car is going to be $15,000. Okay. Okay. And so you can add this cost basically every single year as like an additional maintenance cost that you do. Okay. And of course, what tends to happen is that the cost of breaking down, or the cost of something, or the chance of something happening goes up with time, right? And so older machines tend to not last as long, just because something random might happen and you might that might get destroyed. Okay, so that's another way that you can account for that. And one other factor that you can do is also opportunity cost. Okay. Okay. Because like we said before, there's each year there's newer and better machines that are always coming out, right? And so I think recently the new iPhone just got released, and for some reason doesn't have a charger that comes with it, which boggles my mind, but whatever. And so you can also add an additional cost to your economic life analysis that's associated with, if I don't upgrade this year, I'm losing this amount of money in revenue, or I'm losing this amount in capabilities. Okay? And so that's like an additional cost that you can consider as well. Okay. Okay. Any questions on this? Okay. Okay. So that's economic life analysis. Okay. And so, you know, what we've done so far is basically just compute, you know, if we're buying a new asset, or, you know, we have something that's relatively new, what's the best amount of time that we can keep it in order to maximize our finances. Okay. But that's not really the title of this unit. Okay? So the title of this unit is actually replacement analysis. Okay? And so replacement analysis, what that kind of implies is that you have a machine that's already kind of established or in place, and you're wondering, you know, when is the best time to buy a new one, and what is the best option to get it, or what is the best option to replace that old machine. Okay. Okay. And so basically what we're doing here is we're performing comparison. Okay. And the two things that we're comparing are the economic life and minimum EUAC of a new asset. Okay. Right, so that's one thing that we can do, right? And so let's say that, you know, we're considering the purchase of a new machine. And so, you know, we can look at all the machines on the market and then compute the minimum EUAC and economic life, okay? And so, you know, in order to perform replacement analysis, we have to compare this into an existing asset, okay? And so what we're going to compute for the existing asset is the marginal cost of ownership, okay? And so what the marginal cost of ownership is, it's basically the cost in order to keep this existing machine for one more year. Okay. And so if you have kind of an existing car, an existing, you know, asset, you know, there's going to be a cost that's associated with keeping that thing for, you know, just one more additional year. Okay. And so if we can compare, you know, this minimum EUAC with this marginal cost, okay, then that's what replacement analysis is, okay? Because what we're saying is that if we buy a new machine, if we buy a new machine and then the minimum EUAC or the minimum or the basically that, remember what that represents is the yearly cost that you're going to incur for buying this new machine, okay? If that's less, then if that's less money than what it takes to keep your old existing machine going for one more year, then what you should do is you should replace. Okay. But if the marginal cost is less than the minimum EUAC, then, you know, your old machine is doing just fine, and you can go ahead and keep it running for one more year. Okay. Okay. And so, you know, the next thing that we're going to do is we're going to learn how to actually compute this marginal cost, because there's a little bit to it, although it's not as complicated as minimum EUAC. Okay? But before we get into that, you know, I want to kind of take a step back and talk about some some troubling lines of thought that you can get into when you're talking about replacement, because it's very easy, I think, for us to be in the classroom, or in this case in our homes, and to run the numbers and to say that we should replace something or we should not. Okay, but if you're like me, and you're kind of a little bit resistant to change sometimes, okay, even though that it's not a good thing, you might hang on to something that's for longer than it should, just because you have some sentimental attachment to it. So I think this T-shirt I've had since high school, but the fact that it hasn't broken on me yet or hasn't torn, I still keep it and wear it to this day. I mean, it's just my pajama shirt now, but it's it served me well all these years. But when you're talking about engineering for T-shirts, that's okay. But for big purchases and engineering assets, that's a very kind of dangerous way to think. And so let me give you some kind of some misleading thoughts that you might run into practically, when you start to actually apply this in practice. Okay. And so a lot of these misleading thoughts have to do with sunk costs, right? So if you remember we talked about sunk costs a little bit from the beginning, where sunk costs are the idea that, you spent something in the past, and then that kind of, that sentimental feeling, or that feeling that you need to get something worth it, will kind of drive your current decision making. And you need to kind of block those things out. Okay. All right, so that's exactly what this first thought is right here. Okay, and so I'm going to give these thoughts in kind of quotes that you might hear in practice. Okay. Okay, and so the first misleading thought is, you might have someone say, this machine or this asset cost us, some amount of money. And so because you feel like that initial cost was so great, you're going to want to keep it for as long as you can. Okay, and so what you might hear is that we're not going to replace this until we get our money's worth. Okay. And so when people usually say this, when they say that, I want to get my money's worth for this, they mean that I want to hang on to this for as long as humanly possible, and then not replace it until, it literally just falls apart in my hand. Okay. But the good thing about, what we're doing this week is that you can actually compute with this technique when you're going to get your money's worth, right? So that's exactly the point of replacement analysis and economic life and marginal costs. Okay? And so, when people say this, you can show them the numbers of the calculations that you did to say, I've computed it. If we only keep this machine for 4 years, then we would actually get our money's worth, and we would be time to replace it. So, and so don't let someone saying this, just let that distract away from kind of the numbers, because if you perform this analysis, then the numbers for sure about what's actually your money's worth for this investment. Okay. Okay. Any questions on this before we get into the other two? Okay. All right. So the next line of thought that you might hear, which I'm very guilty of this too, is if it ain't broke, then just then don't fix it. Okay. And so you'll probably hear this line of thought from just from the fact that performing a change or changing something would be kind of, pretty inconvenient. Okay. So to put it in terms of, something you'll probably hear in practice is people probably say that, doing a change or doing a replacement is going to be a pain in the ass. Okay. And so that's true. Changing, something is a pain in the ass, right? But just because it's inconvenient doesn't mean that you shouldn't do it, right? So I'll give you one example where I've totally broken this thing. So I'm using this iPad right now to do the notes, and this is basically the iPad that I got when I was hired here. But it's not that great at actually taking notes, because I don't know if you notice sometimes, but like I'll try to write something and the stylus just won't register on this iPad. So I've been meaning to get a new one, and I actually do have a new one back there, but I just haven't set it up for doing lectures yet because changing it is inconvenient, right? But I know that as soon as I do make that change and I do put in that hour, 2 hour to configure the new iPad, it's going to make a big difference on how these lectures go. So I'm telling you these things to not do, but I'm guilty of this too. So that's just to kind of illustrate that these lines of thought are really easy to kind of get suckered into. But that doesn't mean that you should. Okay, and so the last kind of misleading thought when it comes to replacement analysis has to do with things that don't work well. Okay, and so one quote that you might hear is that people will say that we know that this thing has problems, we know this machine has problems, but we would rather deal with a problem we know rather than a solution that we don't understand. So this was a big one for me in graduate school, because I worked on a lot of code development in grad school, because I do kind of computational work. And so I think everyone in our lab knew that all of our code sucked ass in our lab, and it had issues with lots of different things. But we kind of learned to deal with those issues, like to kind of put it kind of visually. We knew where to put the duct tape on our code in order to get it to do what we want. And so there was never any enough inertia for us to actually write a better code or to actually fix the code. And so we basically, for years, just used broken code, that didn't do what we wanted to, but we could kind of finagle it in order to get it to do that. But that's a really bad, line of thought, right? Because all that time, if you kind of think about it, all the time that you trying to deal with something that's broken, if you combine all that time and kind of put together, that's going to be more time in the end than for the time that you take just to invest a little bit of time up front to replace something. And so just because you know how to deal with, the problems of a certain machine doesn't mean that you should doesn't mean that you should leave it in there. Okay? And so, one last kind of kicker for you to kind of, to encourage, people to replace when they need to, is the fact that basically all equipment gets replaced eventually. And so if all equipment gets replaced eventually, the only matter is when. Okay? Okay. And so are you going to wait until something is really, really bad that's happening, or you just can't stand anymore, or are you going to replace it when it's most economically efficient? Okay, any final questions on this? Okay, so that's all we got time for today. So on Thursday, we're going to pick this up with marginal cost. Okay? And then once we know marginal cost, then we can kind of complete the picture for replacement analysis. Okay. So if there's no more questions, thank you guys, everyone, for tuning in today. I'll see you on Thursday, and have a good rest of your day.
Professor?
Yep. Mm-hmm.
I have a question on my first midterm.
Sure.
You sent me an email a while back saying that my number 8 didn't submit, and then I resent it to you, but it never got graded.
Okay, yeah, I think I might have just slipped through the cracks because there were a lot of adjustments I had to do for that. So I'll do it right after the lecture today, and I'll get to that. So thanks for reminding me.
Okay, thank you.
Yeah. Mm-hmm.
Professor?
Yeah. Mm-hmm.
Would you mind explaining 4C real quick, Professor, for the homework?
Yeah, I can do that real quick. Let me see. I think probably it's best to pull up let me stop sharing here. Okay, let me bring up our. Okay, so 4C, 4C is kind of like I kind of threw the entire boat at you, I guess. And so we had kind of a lot of instances for taxes in this whole thing, right? And so basically for 4C, I'm basically throwing everything at you at the same time. So I think probably the easiest way to go about this is to kind of go column by column and to see, how do we actually compute each one.
Okay.
Okay, so for the year, that one's usually pretty self-explanatory, so that one's fine. And so our before tax cash flow, what I mean by this is basically your revenue, okay? And so let's see, this is 2C, right? So in 2C, right? Our 2C, we have two different options. So you're gonna make two of these tables, right? And so the first table is gonna be for this option right here, right? And so for this option, we have an initial cost of 380,000. We have a maintenance cost of 15,000 per year, and we have a revenue of 140,000. Okay, and so that 140,000, that's our before tax cash flow. So before we apply any income taxes on this project, we make 140,000 per year. Okay, and so for this column right here, for the before tax cash flow, you're going to basically have 140,000 for all the years. Okay.
All right.
Okay. And so the next column here is for necessary expenditures. And so remember, necessary expenditures are basically, any kinds of costs that you need to run your business that basically expire within a year. So things like labor costs, maintenance costs, upkeep costs, stuff like that. Okay? And so we do have a necessary expenditure in this case. And so our necessary expenditure is going to be our $15,000 maintenance per year. Okay? And so we can basically take that $15,000 and we can deduct those from our taxes right away. Okay? And so our necessary expenditures for the first for this first option is going to be $15,000 each and every year. Okay, and so the next thing is the depreciation. Right? So there's two things for the depreciation that you need for this case. Okay? And so the first part is the bonus depreciation, which is 5%. Okay, and so remember what bonus depreciation is that that's the amount of money that you're going to depreciate off the first year kind of right away. Okay? And so at 5%, we're going to take 0.05 and multiply it by initial cost, which is 380,000. Okay, and then we get 19,000. And so our first year depreciation, we're going to add 19,000 to it.
Ah, I see.
And so but that's not the only depreciation in that year, because the other depreciation scheme that we're going to use is straight line. Okay? And so with straight line depreciation, we're going to take whatever's left after the bonus. And so after the bonus, we have 380,000 minus 19,000. So that's 361,000 and divided by 5. Okay. And so each year for the 5 years, we're going to have a straight line depreciation value of 72,200. Okay. And so, go ahead.
Do I add the 19,000 to the first 72,200?
Exactly,
so
right.
Okay, so like for year one?
Yep, so year one, you're gonna have 19,000 plus 72,200. And so you're gonna have a depreciation of 91,200 in the first year.
Got it.
And then for every year after that, it's gonna be 72,200, which is our regular straight line value. So the bonus you only apply to year one. Yeah.
Okay.
Yeah. Okay. So that's the depreciation. And so from there, you can compute your state taxable income. Okay? And so the taxable income, remember, the way that you get that is you take your before tax cash flow and then you subtract your necessary expenditures and your depreciation. So that first year, you're going to take 140,000 minus, was it $15,000 for maintenance, minus the 91,200. Yeah. And so your state taxable income for the first year is going to be 33,800.
800. Okay.
And then the taxes that you pay on that is you're going to multiply that taxable income by the state income tax only. Okay.
6.5. Okay.
Okay. And then you should get 2,197 from that.
Mm-hmm.
Okay. And so after you compute your state taxes, then from there you can compute your federal taxable income. Okay. And so remember, you know, the feds tax you after the states. And that's significant because whatever you pay in state taxes, you can further deduct that from your federal taxable income.
Okay, so I subtracted then.
Yes, exactly. Right.
Okay.
And then whatever's left, that's your federal taxable income. And then you multiply that by 0.21 in order to get your federal taxes off that.
All right, got it.
Yep. And then from there, you compute your after-tax cash flow, and then your book value. You don't really need book value for this one because we're doing a straight line depreciation. But you can keep track of it anyway. So remember, the book value is just going to be your initial cost minus all the depreciation charges to date. Yeah. But yeah, for this problem, you don't really need it because it's you know, you're doing straight lines, so it's the same depreciation charge each year. But you can keep track of it if you want.
All right. Okay. And then when I compute the present worth, so I do like, okay, let's say for the first one, it's like, let's say like negative 380K, and then times the 129,632.72 PA and like the 12%, and then for 5 years. But like, so like one of them is like 133,000. Or do I just subtract that out of like the 129K?
Yeah, so there's lots of ways to do this. So so for the first part of this, where you have the 380K, you can probably do it with the uniform series, but you'll probably see once you do it for the next part, which is the this cost right here. You know, each of the costs in each year are going to be pretty irregular, so it's going to be hard to find a pattern on that. And so the way that I usually do it for after-tax cash flows, that I take each year as kind of a single future sum, and then I bring that back into the present sum. So I
see.
I think I have an example of this at the end of the last lecture. So let me see.
Yeah, I think I saw it too.
Yeah. So it's annoying because you know, you're gonna have to basically do 5 conversion factors, but I think that's kind of the easiest way. And so I basically do something like this. Yeah. So I bring everything. I mean, only just for if you're gonna do present worth, you know, you only need just this first part, right? And so since every year is different, I basically just treat them all as just single future sums, and then I convert them back. So each of them is an individual P over F, and for each of the different years. I think that's the cleanest way to do it, because I think it's more difficult to try to find a pattern to it than something else.
All right, got it.
Yeah.
All right, so because for the second part, if it has a gradient, right? Can I just convert the gradient to like annual cash flow and then just add it to like the revenue?
So this is after the taxes. So after the taxes, it gets a little bit complicated because. You know,
okay.
Yeah. So if you can find that pattern, that's great. But I wouldn't, you know, I wouldn't waste that much energy trying to find that, because I think sometimes it's easier just to treat them all individually. But if you can find a gradient value for it, then that's I would say go for it. But I think for that one, I couldn't find a gradient for it.
Okay.
Yeah. So I just treated them all individually.
All right, got it. All right. Thank you, Professor.
Yep.
Have a good day, Professor.
Thanks. You too. All right, Josh, did you have any more questions? I'm gonna go look up your answer right now.
No, I'm good. I was just tuning in for question 4.
Okay. Okay, so I'm gonna end the call. I'll be in office hours in 5 minutes, but I'll grade your thing and then I'll put it up on Canvas right now.
Okay, thanks.
Yeah, thanks again for reminding me. It kind of slipped through my mind.
No worries.